Okay, so thank you everyone for joining the week 12. That is the last week of problem solving session. This particular course is on unsaturated soil mechanics, and this week content is mainly related to the volume change behavior and demonstration of the laboratory experiments. And this course instructor is Dr. Weaver from IIT Guwahati, and my name is Satyam Tiwari, and I'm a PMRF here for this particular problem solving session. So before we start, let's wait for 1 or 2 minutes so that others can join in the meeting, and then we can proceed further. So now I think we can start, and in this particular class, we'll mainly try to focus on solving some of the numericals which we have solved earlier, and so that we can revisit the concepts of this whole course that will help you in the examination. And then we'll be coming up with the assignment problems, and we'll try to solve them. So let's say this is one of the questions that in a consolidation test, the following results have been obtained when the load was changed from 50 to 100 kilometer per meter square, and the Y ratio changed from zero point 0.7 to 0.65. So we need to determine the coefficient of volume change, that is the LMV, and the combustion index CC. So how we can do that? So for that, as we note here that the E naught is zero point 0.7, then the E1, which is after some the change in the load, is 0.65. The sigma naught dash as bar at first loading was 50 kilonewton per meter square. Then it has been changed to 100 kilonewton per meter square, right? So first, let's say we determine the coefficient of. So as we understood that we have the values of E naught given, and E1 is also given from 6.5. Then apart from that, we have the values of sigma. We have the values of sigma naught bar, that's given 50 kilonewton per meter square, and the sigma bar, that's given 100 kilonewton per meter square. These values are given. Now first we'll determine the coefficient of compressibility. That is nothing but the value of AV. It is determined by delta E upon delta sigma. Okay. And if we ignore the sign, then we'll obtain the values at zero point 0.7 minus 0.65. That will be divided by 100 minus 50. So if we calculate it further, then we'll get zero point 0.7 minus 0.65. That's going to be 0.05 to be divided by 50. Solving it further, we will get zero point 0.05 divided by 50 to 0.001 meter square per kilometer, right? Because the unit of sigma is kilometer per meter square. The next thing which we need to calculate is the value of this MV, that is the percent of volume decrease. Okay, so the formula for MV is AV upon 1 plus E naught that we have seen earlier also. The value of AV is 0.001 and the value of 1 plus E naught is zero point 0.7. So it will be resulting in 0.001 upon 1.7, which is nothing but 5.88 into 10 to the power minus 4 meters square per kilonewton, right? Based on this value, we can determine the coefficient of this compressibility index, compression index, that's compared by E upon uh, delta of log sigma, right? That is the slope in E versus log sigma curve. So it will be 0.05 in the numerator and below it will be 100 minus log at the base 10, 50. Let's solve this one. Let's see what you obtain. Or you can also write it as 0.05 divided by log at the base 10, 100 upon 50. That will give you log at the base 10, 2. So it will be 0.050. Log at the base 10, 2 is 0.301. And it will result in an answer of 1.166. So we have obtained two values which we needed, MV and CC, right? So I hope this one is clear to you. Okay, moving further to another question that we have seen in other class that at relative humidity 50% and a air pressure of 100 kPa, which temperature leads to a higher air density, 0 degree or 45 degrees Celsius? Given that molecular mass of the dry air WA is given as this, and the universal gas constant is already known, and the molar mass of the vapor is also known. So how we can calculate it? We have seen earlier that the formula for the dry density of air at will be formula for the dry density is equal to UD WD upon RD, right? But if we want to calculate it at particular moisture content, then the formula changes to this dry state minus 0.611 WA upon WV minus 1 exponential of 17.27 T minus 273.2 upon T minus 36 multiply WV RH upon RT, right? So let's calculate number one for T is equal to 45 degrees Celsius. That will result in 318.2 Kelvin, right? So it's nothing but 45 plus 273.2 Kelvin. Hmm. So it will give you 318.2 Kelvin. So if you calculate the air pressure, this density and the dry state, then it will be equal to UD WD upon RT. The value of UD is given as 100. Okay. If you calculate it into the Newton, then it will be into 10 to the power 3 Newton per meter square. The second term that is given is negative. That will be equal to 28 point or dry air. The molecular mass is given as 28.966 kilogram per kilomole. So it will be multiplied by 10 to the power minus 3. So kilogram per mole. Okay. And we can divide it by the value of RT. RT is nothing but 8.314 Newton meter upon mole Kelvin, right? And further it will be multiplied by the temperature, that's given 308.2 kelvins. So let's calculate it, how much we are getting. 10 to the power 5 multiplied by 28.966 multiplied 10 to the power minus 3. It will be further divided by 8.314 multiplied 318.2. So this will give you a value of 1.095 as the density per kilogram per meter cube, right? And now we need to calculate it at a particular moisture or the relative humidity of 50%. So sigma A moist, this formula will be used as given above. So rho D 1.095 minus 0.611. That is the W is the air density, the molecular mass of air, the dry air, that is 28.966 upon molecular mass of the vapor. Okay, so that will be 18.016 minus 1 into exponential 13.27 multiply the temperature is T minus 273.2 is temperature in degrees Celsius we can say. That is 45, then it will be 318.2 minus 36. And the outside will again have the V, so it is given as 18.016 again, multiplied by relative humidity is 50%, so zero point 0.5, and the air constant 8.314, that will multiply by the temperature 310.2. So now we need to calculate this value, and how we can do that? 1.095 minus the first term will be 0.611 multiplies 28.966 divided by 18.016 minus 1. So it will be 0.370 multiplies exponential e to the power 13.27. So it will be exponential 13.27, that will be multiplied by 45 divided by 318.2 minus 36. We'll close the bracket and we'll obtain 8.298. That it will further multiplied by 18.016 multiplied by 0.5 divided by 8.314 further divided by 318.2. So it will be 3.405 10 to the power minus 3. Solving it further, so a moist we will get 1.095 minus 0.370 into 8.298. That's 3.405 into 10 to the power minus 3. So it will be 1.084 something kilogram per meter cube. Right? So sigma moist we have got this value. Okay. So that is the for a temperature of 45 degrees. Now let's see if we solve it for the other temperature that is given at 0 degrees. So what we'll get, now this temperature will change, right? Let me erase things which will change. This UD will remain constant, WD will remain constant, R and this P will change. And then further, if we'll see here, so WWV, everything remains constant, just this temperature thing will change, and this temperature will also change. So based on this, the value, these two values will change, right? So let's see how we can do that. Rho D will calculate UD, that is 100 kPa, multiplies WD, 28.96 into 10 to the minus 3 upon R is given The temperature here is 0 degrees Celsius, so it will be 273.2, that is 0 plus 273.2. Okay. So based on this, we'll get 40 as 100 into 28.966 multiplied 273.2 upon 8.314. So that's going to be 1.275 kilogram per meter cube. Putting this value here, we will obtain this one is 0, and that's going to be 27, 273.2 minus 36, and here it will be 273.2. So this exponential term, that's going to be equal to 0, that's going to be 1, and here 18.016 multiplies zero point 0.5, that will be divided by 8.314 multiplied to 73.2. So it's nothing but 3.96 into 10 to the power minus 3. Solving it further, we'll obtain 0.095 minus 0.37 multiplies 3.96 into 10 to the power minus 3. So how much we are getting? We are getting 1.274. Okay, so 1.274, and previously we have got rho A minus as 1.08. This is at a temperature of 55 degrees Celsius. This is at a temperature of 0 degrees Celsius. So it was asked that which temperature leads to higher air density. So the higher air density is obtained at a lower temperature. Right. So please have a look at this question. Let me know if there is anything that you're not getting here. Okay, all right. So moving on to our next question. That's basically on the viscosity. So viscosity is a material variable describing the ability of a given fluid to resist flow. So the example on the viscosity is such that a liquid and a gas conductivity testing was conducted using separate constant at per meter for sandy soil with a core mean pore size of 10 to the power minus 3 meter. The steady state velocity of air through soil is 10 to the minus 2 meter per second, and that was a water of 10 to the minus 4 meter per second. So, in determining whether the room temperature Darcy's law can be used to analyze the test results, and we need to consider the velocities of air and water at room temperature to be 1.8 and 10 to the power minus 5 kilogram per second meter and zero point 0.9 into 10 to the minus 3 kilogram per second meter respectively. The density of air at room temperature is about 1.2 kilogram per meter cube, and that of the water is about 1000 kilogram per meter cube. Right. So, how do we determine that if the Darcy's law is valid or not? So, one of the parameters that can define this Darcy's law is the Reynolds number. The Reynolds number is defined as rho mu d upon mu, right? So the value of rho for is given as 1.2 kilogram per meter cube. The value of velocity is given as steady state velocity is 10 to the minus 2 meter per second. And the value of d is the mean pore size, that is 10 to the minus 3 meter. That will be divided by the dynamic viscosity. And this is given as for air is 1.8 into 10 to the power minus 5 kilogram per second meter. So how much we are getting? 10 to the power minus 2, 10 to the power minus 3, 10 to the power minus 5. Those will cancel out. 1.2 upon 1.8. It will result in 0.67, right? Then this is for the air. Now let's see for water. For water, Reynolds number will be again rho Vd upon mu. So it will be the value of rho for water is 1000 kilogram per meter cube. Multiply the velocity value that is given as 10 to the power minus 4 meter per second, and the value of this t, that is the pore size, 10 to the minus 3 upon the value of mu is given as 0.9 into 10 to the power minus 3. So 10 to the power minus 3 and 10 to the minus 3 will cancel out. This will result in 10 to the power minus 1 upon zero point 0.9. So that will be zero point 0.1 upon zero point 0.9. It will give you 0.11 RE. So as we have seen earlier also, if this is the profile of a specific discharge versus hydraulic gradient, and in that case, up to a Reynolds number of 1, this will remain linear laminar flow. Okay, after that, the nonlinear laminar flow and turbulence flow will come into picture. So if the Reynolds number is less than 1, this will be laminar flow, and thus is law will be valued. So in both the cases, the RE is less than 1. So okay, thus law is valid for this question, right? So moving on to the next question. Here we have direct shear test. So the shear walk test results of two samples of the same soil with the different initial unit weights. It's a shear walk test result of two samples of the same soil, but the different initial unit weights are shown in the table below. And sample A did not show a peak value, but sample B did. And we need to determine the internal friction angle at a critical state and the peak internal friction angle at two vertical loadings. Okay, the dilation angle at same vertical loadings for sample B. Okay. So let's see how we can find out. So for solving this question, first we need to uh, make a plot. So it's better to use Excel for that. So in the y-axis, in the x-axis, we can have vertical force component, And the y-axis we can have horizontal force component, right, in Newton. So here it will be 200, 400, 600, and like that. Here also it will be 200, 400, 600. It's like that. So if we plot the test A results first, then we'll see the first one is having horizontal force 150, vertical force 250. So the horizontal force 150 will be here, 250 will be here somewhere, right? That's it. The vertical force 250 will be here, and the horizontal force 150 will be here somewhere. So this is the point one. Then the second one is the vertical force is 500 here, and the horizontal force is 269 somewhere here. So for the third point, 750 and 433, we will have 750 and 433. So if we join these three, we'll get a best fit line here. That will be for soil A. Okay. And if we calculate the angle of internal friction for this one, then this will come around 30 degrees, right? 30 degrees in the Excel. Now, if we plot these points for soil B, then we'll obtain this graph will be something like this. Okay. So this behavior is obtained, that is the peak behavior, right? So in that case, the value which you obtained here, that is phi dash critical state. Okay. Now, if we need to calculate the phi dash peak, so if we are calculating phi dash peak at a loading of 200, then we can obtain it by just taking a tan inverse the horizontal force at 200, that is 175 upon the horizontal force 200. So it will give you a value of tan inverse 175 upon 200 is going to be 41.18 degrees. Okay. Similarly, we can do it for phi dash peak at 400 Newton. So that will give you tan inverse at 400 Newton. The value of horizontal force is 248 divided by 400. So it will give you tan inverse 248 upon 400. So it's got to be 331.79 degrees. Moving on to the further, moving on further to next step. Now we need to calculate the dilation angle. So number one, the dilation angle is going to be phi dash P minus phi dash critical state. So for this vertical force of 200 Newton, if we calculate alpha P at 200 Newton, that will be equal to phi dash peak 41.18 minus 30 degrees. So it will give you 1.18 degrees. Similarly, for 400 Newton force, alpha P at 400 Newton is going to be 31.79 minus 30. So it's going to be 1.79. Okay. Here it's going to be 11.1. Sorry. Right. So we have determined the critical state shearing, the greatest internal angle of friction, then the peak internal angle of friction at 200 and 400, and thus this dilation angle at 200 and 400 Newton. Right. So I hope there's no problem in this question. Please have a look once. Okay, so let's move on to the next question. We have a question that currently the relative humidity in the environment is 80% and the temperature is 22 degrees Celsius. So we need to determine the dew point temperature for the given conditions. Okay. So how we can do that is first we will need to calculate this vapor pressure at saturation or vapor pressure at saturation. So that will be equal to the formula, Tatton's formula we'll use 0.611 exponential 17.27 T minus 232.2, sorry, and T minus 36. That's going to be Tatton's formula from 1930s, I think. So let's find it out. The T is given as 22 plus 273.2. It's going to be 295.2 Kelvin. So this UV sat will be equal to at 22 degrees Celsius. It's going to be 0.611 exponential 17.27. Here it will be 22 upon 295.2 minus 36. So let's solve this one. Let's see how much UV set we are getting. So let's write exponential 17.27 multiplied by 22 upon 295.2 minus 36 into 0.611. So it will be 2.64. The unit will be kPa. Right. Now we have the relative humidity as 80%. Okay. So in that case, the UV sat value in kPa is going to be zero point 0.8 times 2.64 into zero point 0.8. That's going 2.117 kPa. Next, UV sat kPa at point B, that is the dew point, because we are moving from this point A to point B by decreasing temperature. We need that if we equate to UV sat kPa at A, then it will be 117 is equal to 0.611 exponential 17.27 multiply small t if we write in degree Celsius, that's going to be T plus this one will be 273.2 minus 230 minus 36. Okay. So if we solve this one, then we will get a temperature of 18.39 degrees Celsius. Okay. So to reach the dew point temperature, we need to decrease the temperature for 22 degrees Celsius to 18.39 degrees Celsius, right? So please have a look at this question if you have any doubt in this one. So we have discussed about the numerical of finding out the dew point temperature for the given conditions. Now we will deal with the surface tension as we have discussed earlier in the previous lectures. So let's say the example is that assume that air-water interface for a certain degree of saturation among the particles in the fine sand, which is spherical, and it varies from zero point 0.1 to 0.001 mm diameter. So if the surface tension of the water is given at 25 degrees centigrade and Celsius and the pore water pressure is given, then what will be the range of pore water in the unsaturated sand? Okay, that we need to determine. So we need to determine the UV max as well as UV min. So what it will be? So as we know, the formula for the matrix section, that is nothing but UA minus UW, that is equal to twice TS if cos alpha is taken as 0, cos alpha upon R max or R, right? So if we do need to determine the maximum value of UW, if we rearrange it, then we'll get UW is equal to UA minus twice TS upon R max, right? Sorry, R. Then if you want to get the maximum value of UW, then this R should also be maximum, so that this term will be minimum. Okay. So let's see, we are determining the UW max. It will be equal to UA minus twice the surface tension upon R maximum value. So the UA value that is given here for air pressure is 100 kPa minus 2 times the value of the surface tension is given as 72, that is millinewton, so 10 to the power minus 3 Newton per meter at 25 degrees Celsius upon the R max value. The value of spherical particles are given as 0.1 to 0.001, the diameter, fine and spherical in diameter. So we'll divide it by 2. So 0.1 that will divide by 2. That is in mm. Okay, we are converting into meters. So into 10 to the power minus 3, right? So if you calculate it, it will be 100 minus, let's calculate this one. People try to calculate also. 144 into 10 to the power minus 3 divides by, this one is going to be 5 multiply 10 to the power minus 5. Okay, and also as we are doing everything in kPa, so we'll multiply it by 1 by 1000 to convert it, because this one is Newton, right? So we'll divide it by 1000. So let's see what we'll get. 100 minus 144 divides by 5. These are going to be 10 to the minus 6, 10 to the minus 5, so it's going to be 10 to the minus 1. So it's 28.8 into 10 to the minus 1, it's going to be 100 minus 2.88. It will give you 97.12 kPa. That is what's written here also, right? So we have determined the maximum value of the flow pressure. To determine the range of the flow pressure, we also need to determine the minimum value. What it will be? UW minimum, that will be equal to UA minus twice TS upon R min, right? So everything else will remain the same, just that the value of R will change. What is the value this time? It's going to be 0.001 divided by 2 into 10 to the power 3. So it's, I think, 0.01, right? So only one zero is there, not the decimal. So then it will be divided by 1000 to convert to kPa. Let's see what we are getting. 100 minus 2 into 72, 144 into 10 to the power minus 3 into 10 to the power minus 3 upon, this one is going to be 5. This one is going to be 5 into 10 to the power minus 6, right? So if these will cancel out. So 100 minus, if we solve this one, we get 28.8. So it will be 71.2 kPa. So the value of UW max is this one, UW min is this one. So what will be the range? UW max then minus UW min, that will be the range. 97.12 minus 71.2. So how much will get? 0.12 minus 71.2. So it will be 25.92 kPa. That will be the range, right? So please have a look at this question and let me know if you have any difficulties. So I think everything is fine in this one. Let's see the one more numerical. That is a problem for example from the book of Blue and Lucas. And this example says the table 1.11.1 that is given here. It shows the results obtained from a series of digit wall constant hydraulic conductivity tests. These are conducted on unsaturated soil specimens. Those are of sand. The length and diameter of the cylindrical specimen are 10 and 6 centimeters respectively. Constant head was maintained across the specimen such that the pore water flowed from top to bottom. The first two columns of the table 11, that are these, show pore water head measured at the points located inside the specimen with tensiometer probe inserted near the top and bottom, respectively, separated by distance delta L that is equal to 8 centimeter. The third column shows the volumetric flow rate measured for the specimen for each test at steady state condition. Okay, the identical specimen were prepared for the eight tests and the pore air pressure was maintained at atmosphere for these. Then we need to calculate the hydraulic conductivity function for the sand. Right. So we have been provided with these three columns and we need to calculate these three, right? So we need to calculate the head difference, then the hydraulic conductivity function, okay, and the average heat. So actually, we need to calculate the hydraulic conductivity function only. Mhm. So how we can do that? For doing it, first we have to see what data do we have. Okay. So we have the data regarding the head. Okay. Then we have the sample dimensions. Okay. So let's first find out the area of the sample. That is pi by 4 into a square. There is the pi by 4 into d square. D is the diameter. So length and diameter are provided. That's going to be pi by 4 into 36, 28.27 centimeter square. Right. Now we need to calculate. We already know the value of delta L. It's nothing but 8 centimeters. Okay. This is delta L, not delta H. And the delta H we will calculate here. So what will be the delta H? Delta H will be H1 minus H2, the head difference, if we ignore the sign. Then it will be minus 0.51 plus 15.81 for the first reading, for the first test. So that will be 15.81 minus 0.51. So it will be 15.29. So it's 15.30 almost. The next, if you want to calculate the H average value, then it will be nothing but minus 0.51 plus minus 15.81. That will be divided by 2. So it will be 0.51 plus 15.81, both in negative sign, divided by 2. So it will be 8.16. Right? So average at 8.16 if you ignore the sign. That's actually minus 8.16. So as to determine the value of hydraulic conductivity function, that is the K. So if you see the formula of Q is K into I into A. So if we write at the place of I, we write delta H upon delta L into A. In that case, the value of K becomes hydraulic conductivity function Q times delta L upon delta H times A. And it will result into the value of Q. Let's say for first experiments, it's going to be 1.30 into 10 to the power minus 1 centimeter cube per second. The value of delta L is 8 centimeters. Everything is in centimeter and second. Value of delta H we have find out 15.30 in centimeter, and the value of A we have become in here as 28.27 centimeters square. So let's find out how much we are getting. 1.3 into 8 into 10 to the power minus 1. That will be divided by 15.30 multiplied 28.27. So we get 2.4 2.4 into 10 to the power minus 3. The unit will be centimeter per second. See, this one is for test 1, right? Please have a look and let me know if there's any problem in this one. Now, the similar thing we can do for other test also, right? Let's do it for one more test. So test 2. So delta H will be minus 1.02 plus 25.50. That will result in 24.48 centimeter. And here we'll calculate the value of H average. That will be minus 1.02 minus 25.50. It will be divided by 2. So 1.02 plus 25.50. That will be divided by 2. So we'll get 13.26 centimeter. And if we calculate the value of K from this formula, then we will get Q times delta L upon delta H times A. So we'll get the value of Q is 1.42 into 10 to the power minus 1 multiply 8 upon delta H is going to be 24.48 multiply 28.27. So let's see how much we are getting. Multiply 8, that will be divided by 24.48 multiply 28.27. We are getting 1.654 times 10 to the power minus 3, 1.64 times 10 to the power minus 3 centimeter per second. Okay. So it's the same as written here. So for the two tests we have determined, and similarly we can determine for other tests also. That will give you the variation in the values of hydraulic conductivity based on these facts which we have observed. Um, can you please check the calculation if there are any errors? So let's move on to our next question, which is based on the prediction model for soil water characteristic curves. So a horizontal soil column is soil is sample is there where the head at one end is maintained and that's not because of the height difference from one end to other end. The water starts flowing from here to this side, right? So the example says an infiltration experiment was conducted in the horizontally sandy soil column shown in the figure. The cross section area of the column is 100 centimeters square. And the cumulative infiltration volume after 20 minutes of testing is 200 centimeter cube. So Q is given 200 centimeter cube. Then we need to predict the infiltration rate, cumulative infiltration at 1 hour and 6 hours. Okay. So let's see how we can solve it. So for solving this problem, we need to determine the infiltration rate at a particular two time instance. Okay. So first, what will determine the quantity or property that is called as sorptivity. Sorptivity is defined as Q upon under root of T, and the Q is nothing but the this infiltration per unit area. So we'll write 200 centimeter cube, and the area from which this infiltration is happening is 100 centimeter square. And that will be multiplied by under root of time. The time given for this is 20 minutes, 20 into 60 seconds. So what we'll get? We'll get 2 upon under root 20 into 60. So we'll get 0.0577. And that's going to be in centimeter per under root second. Fine. So based on this objectivity value, uh, it's said that this it is assumed that this objectivity will not change over the time. Okay, so we can assume that this objectivity will remain constant. So then we can determine the infiltration rate at 1 hour and 6 hours. So first we'll determine the cumulative infiltration that will be S under root T. It will be equal to, let's say, at 1 hour. So S under T is equal to 0.0577 multiplied by the time is 1 hour into 60 minutes and 60 seconds. 0.577 into 0.57, sorry, 0.0577 multiplies under root 3600. That's going to be 3.46. The unit is centimeter per under second. So now if we need to determine the weight, then Q will be dQ upon dt. So it will be nothing but 1 by 2 under root T multiplied by S. So it will be equal to 1 upon 2 into under root 3600 multiplied by the S is 0.0577. So it will give you a value of 3 value of 3 point, sorry, 1.74 centimeter per hour. So we converted second to hour. Okay. Let's do it for 6 hours. So again, the Q will be defined as S under root T. It will be 0.0577 under root of 6 into 60 into 60. It will result into, let's find out, 0.0577 multiplied under root 6 into 60 into 60. So it's going to be 8.48 centimeter. Now the rate will be dq upon dt. 1 upon 2 under root p into s. Solving this one, we'll get 0.0577 upon 2 times under root 6 into 3600 is equal to if you convert into centimeter per hour, then it will be 0.71 centimeter per hour. So after 1 hour, the infiltration rate, the rate is 1.74 centimeter per hour. After 6 hours, it got decreased to zero point 0.7 centimeter per hour. Okay, please have a look at this question and do let me know if you have any doubt. Further, in the prediction of salvator characteristic curve, we have studied several models by which we can fit the data of the salvator characteristic curve and make a prediction model based on your observed data from the laboratory. One of the basic model is broken Corey model, provided in 1964. This model is a uncontinuous, that is not continuous model. So till the suction reaches this bubbling pressure point on the air entry pressure point, the theta is defined as the volumetric water content is defined as the theta saturated. Okay, so if we like plot here, then this one is theta, this one is suction. So till the bubbling point is reached, it is calculated as theta suction, theta s. Right. After that, it will follow certain trend. Okay, this one is 5b, right? So it's like that only. Till this point, it will be a just a straight line with theta s. Okay. So in this equation, if we provide the values of theta r, theta s, theta r, and we also provide the value of phi b that is known for a particular soil, then we can determine the relationship between theta and phi, that is the soil water characteristic. But here there is one parameter lambda, okay, that needs to be fitted for a better fit in the data, right? So, for example, if we have this data of particular metric section and if not theta, then we can have the data of this saturation, degree of saturation value also. So if we plot it here, degree of saturation versus metric suction, then these data points will be shown like this, right? And if we now try to fit a curve using Brooks and Torrey model, then we'll obtain this kind of curve. And for this particular best fit curve, we can determine the value of lambda. Okay, we can vary the value of lambda, and then we can see how better it is fitting the data set. Okay. In this way, we actually determine these values. Okay, so in this way, what we can do is that based on the laboratory data, we can fit these curves, and then we based on the beta fit curve, we obtain the value of lambda. Okay, and the phi b is already known, and the SAR is already known. So This numerator we have solved using an Excel sheet. That's because we can use the solver tool to find out the most optimal value of lambda. So we have obtained lambda as 1. Then we have other models also, like one of the model is Friedland and Zing model that's provided in 1994. Based on this model, we actually write the relationship between theta and psi as theta is equal to c psi, that c is a function of psi. Okay, this matrix option, and multiply theta as 1 upon ln e plus theta upon a. So this expression, if you'll see, is not convertible. So you can write theta in terms of phi, but you cannot write phi in terms of theta. So this is not convertible. Other expressions like here, Brooks and Corey model is convertible. You can write theta in terms of phi and phi in terms of theta. Right. So here this C is provided here. So we can take C from here and use it here for to determine the value, the relationship between theta and psi. Okay. So this is one of the examples which we have solved. If we see on the table 12.2, then we'll obtain the value of matrix suction versus volumetric water content here, right? And this actually gives the water characteristic curve. And when we fit the Brooks and Corey model here, sorry, this Fedland and the Zing model here, then we will obtain a relationship that will equate, that will give you the value of water content based on the matrix suction or the matrix suction based on the water content, right? So like here there are two soils. One is the silty loam and one is the glacial till, and we have the data for both laboratory data. Then based on this laboratory data, we can actually determine the better fit parameters, and these parameters will give you a curve that will the best fit for this particular data set. So I hope it is fine. Now, before we move on to devise this pedal transfer function using our Paris function method, we'll take a short break and then we can start from here again. So let's start with this artificial method, and let's understand it with an example that how we can obtain the Peter transfer function. So using this method, then we have a particular soil, the specific gravity for which is provided, and we also have been provided with the dry density of that particular soil, and this percentage finer and is also provided. So let's understand how we can solve it. First step is to determine the white ratio. Okay, so while determining the white ratio, we will use this formula, that is rho s minus rho d upon rho d, right? If you simplify it, then we'll obtain rho s upon rho d minus 1. Right? So here the value of the dry density, that is rho d, is given. We need to determine the rho s. So as we know by the basic properties of soil, basic formulation, that rho d is nothing but gs rho w upon 1 plus E. The GS rho w is nothing but the dry density of solid, right? Solid. So rho S can be determined from here. The rho S will be rho D times 1.4 into 1 plus E, the white ratio at 1 plus E, right? Now, if we let's write it as rho D, if we solve it further, then we'll obtain that E is equal to rho s upon rho d minus 1. So we have reached at this equation. Then from here we can reach here, right? So in this way we can obtain the value of void ratio. So let me just erase this. So in this example, if we try to solve the for the void ratio, then the void ratio will be equal to rho s, that is rho s upon rho d minus 1, right? Rho s is nothing but gs into density of water. 2.67 into 1 if we are writing in gram per centimeter cube. Then the dry density of the soil is 1.4. And this will be subtracted by 1. So 2.67 divides by 1.4 minus 1. So that will give you 0.907. The white ratio we have calculated. Okay. Then to calculate the pore volume is the next step, where we'll calculate the pore volume using the formulation Mi at particular location upon E that we have determined upon rho s that we already know. But how we can determine the mass, solid mass per unit sample in the ith segment? Then we have to determine the one final fraction in the Ni plus 1th section minus Nith section divided by 100. Okay, so Ni plus 1th section is 11.866 minus Nith section is 10. That will be divided by 100, so it will give you 0.11.866. That's going to give you 1.866 divided by 100.1866. Okay, so if we use that here, then we'll obtain this VI is equal to MI, that is 0.01866, or I think it is 0.0186. And then we have the void ratio we determine 0.907. It will be divided by rho s, that is 2.67 multiply 1. So how much we'll obtain? 0.01866 multiplies by 0.907, and we further divided by 2.67. We'll obtain this value as 0.00633, and this is the unitless quantity. This is also unitless. Rho s is gram per centimeter cube, so it will be centimeter cube per gram. Okay, so we have discussed about the void ratio, then we have discussed about the pore volume, and now the third thing we need to discuss is to determine the volumetric water content, the formula for which is given as theta vi is equal to summation of vj at every step, and this sample bulk volume per unit sample mass. Okay, so how we can calculate that is that we can write theta vi is equal to vvj. We calculate this pore volume in the last step, that is going to be 0.0063, right? And then we will divide it by the sample bulk volume per unit weight. So how we can determine the sample bulk volume? For per unit sample mass, it's going to be mass upon density. So for per unit, it's going to be 1 upon rho d. Rho d we have already determined here. That's going to be 1.4. So we'll multiply it by 1.4. Let's see how much we are getting. Okay, so multiply it by 1.4, so 0.0063 multiply 1.4, that's going to be 8.82 into 10 to the power minus 3. Okay, this will be equal to 0.0088. Okay, this is a volumetric void ratio. In the next step, we want to calculate, till now we have calculated the void ratio, then we have calculated the pore volume, then we have calculated the volumetric water content. Now we move on to calculate the pore radius, that is given by small ri, and it will be equal to the capital Ri multiplied by this term 4Cni 1 minus alpha upon 6 to the whole power 0.5. Let me make some space by erasing this. Okay, so let's calculate this small r. Small r is equal to capital R, and that will be multiplied by 4 times Cni to the power 1 minus alpha upon 6 to the whole power 0.5. So let's calculate how much is this. The capital R, that is going to be the average particle size that we can calculate here, and before that we will calculate the value of Ni. This number Ni is given by 3 times Mi, which we calculated earlier, upon 4 pi rho s r1 to the power whole cube. The 3 times Mi is given by 3 into Mi is nothing but what we calculated here, that is going to be 0.0186 4 into pi into 4 into pi into the term rho s. The rho s is nothing but 2.67 multiply 1, and further we'll multiply it by the Ri. Ri is the average value of the radius. So the average value of radius is 0.001 plus 0.002 divided by 2, that will be the diameter, multiplied by 2, that will be the radius, right? And the whole cube. So let's find out the value of Ni. It will come as 3 into 0.0186 divides by 4 into pi multiplied by 2.67 multiply 0.001 plus 0.002 upon 4 to the whole power 3, and this bracket is closed. So it will come at around 3942,114.94. Fine. This one. Based on this, if we calculate this Ri for a particular iteration, then we'll calculate the capital Ri, that is we have calculated already here. Now this thing, that's going to be 0.0075, that will be multiplied by 4 times this C value. Okay, so this actually is E, right, not C. So wide ratio, the E value is, we have calculated here 0.907 into Ni value we calculated 3942114.945, and that will be to the power 1 minus alpha. Let's say we are taking 1.4, okay, and divided by 6 to the power 0.5. Let's calculate how much we are getting. 4 into 0.907. Could you please help me in that one? 3942,114.945 multiply and to the power 1 minus 1.4. Okay, this much. Then it is divided by 6 to the whole power 0.5 and multiplied by 0.0075. Okay, so how much we are getting? We're getting 2.796 into 10 to the power minus 4. This will come in same value as this mm, this Ri. And then based on this we can also calculate the suction head or the value of suction. Then we'll calculate psi as twice Ts cos beta, that's going to be 1, and this rho Wg will come here, so Ri, that will be equal to 2 times the Ts is 72 as we know, upon this Ri value is given as 2.795 into 10 to the power minus 4 something, right? So based on this we can calculate 2.72 upon 2.795 and something like this we will get 5.152 Newton per mm square. Okay, so we started from these values, and these particles are distribution, and we reached out to the value of psi and also the value of theta. So by here we can calculate this as WCC, soil water characteristic curve. So that's what this Arya-Bayes method was about. If we have the information about the particle size distribution and the basic geotechnical soil properties, then based on that we can calculate the soil water characteristic curve, or the relationship between the suction and the volumetric water content. Please have a look at this problem and do let me know if you have any trouble. Please recalculate by yourself so that you can know that where you are facing trouble. Okay, so let's see this problem, that at a particular site the steady state flow of water is taking place in vertical direction. The flow rate of the water due to the evaporation is given. So basically we have been provided with the value of Q, that is 10 to the minus 8 meter per second. The drying rate of the volumetric water content, metric suction head, theta, hm. The permeability of different samples are provided in the table. And we need to calculate the height at which these particular heads will be occurring, right? So how we can do that? We know that formulation which we have talked in theoretical class, minus dz is equal to dhm upon 1 plus q by k. Okay, we'll be using that one only. So let's say for the first one, okay, this occurs at 0, depth from the top is 0. Okay, let's say for the second one, so if we determine the dz, okay, so this is, let's say, dz, so it will be calculated by minus dhm. What is the head difference? Head difference is given as minus 0. This h1 minus h2. Okay, and this is already in minus upon 1 plus this q, that is given 10 to the power minus 8. It is actually coming into the soil, so its infiltration, that will be minus. Okay, and then it will be divided by the k value. K value is nothing but 5 into 10 to the power minus 7, right? So I think this one is written wrong. This one is going to be 4 into 10 to the power minus 7, so we will write 4 into 10 to the power minus 7. So let's see if we calculate how much we are getting. We are getting as 1 minus, and the term is minus 10 to the power minus, so that's going to be minus 10 to the power minus 8, and it will be divided by 4 into 10 to the power minus 7. Okay, so that's going to be minus 1.025 dz. Okay, so if we write it here, I think we have missed something. Okay, so we need to take the value of denominator also. It's going to be minus 0.001 plus 0.5, and then we divide by answer, so it's going to be 0.486 approximately. So we'll write here 0.486, right? And this will be minus, so here we'll get the capital Z, that is cumulative, is 0.486. We are neglecting the sign of these values. Let's do that. Do it for one more step. So how you do it? The dz for the second step will be minus sign, and it will be minus 1.5 minus that's going to minus 0.5 minus minus 1.5, that is h1 minus h2, and it will be divided by 1 plus 10 to the power minus 8 in minus, and upon the value is given as 3 into 10 to the power minus 7. So how much we are getting? We are getting minus 0.5 plus 1.5, that's going to be minus 1 upon 10 to the power minus 8 upon 3 into 10 to the power minus 7. Okay, 1 minus answer and 1 upon answer. So if we calculate for the second step, we are going to have this one is also wrong, I guess. So it's actually given as 2, so we'll write it here as for the second step it's 2. So if you calculate this one, you will be getting 0.5263. So minus 0.5263, and here if we calculate 0.486 plus this one is going to be 1.0344. Fine. Okay, so in this way you can keep on calculating the value of capital Z, and by calculating the value of small z, right? So this is a good example to determine the location at which this particular h will be occurring. Okay, so let's understand this problem we have studied as the value of this x, the location is provided, that is a horizontal infiltration test. Value of theta I at that particular location is provided, and then the value of lambda I is provided. By first what we need to do is that at the end we need to determine the diffusivity function d theta. Okay, so first we can do is we can determine ai, that is the area at that particular iteration, that will be equal to theta I minus 1. So let's say if we calculate here for these two, then we get 0.04 minus 0.02 in one bracket, and then we get lambda I plus lambda I minus 1, that's going to 1.958 plus 1.962, and this will be divided by 2, so it will give you 0.04 minus 0.02, and this will be multiplied by 1.958 plus 1.962 upon 2, and it will be equal to 0.0392, this one, so 0.0392, and the cumulative increment will be the value before that and this. Okay, so this also we can determine, right, this one. And now we need to determine the Boltzmann variable function Si, that is equal to d del theta upon del lambda I. So it will be it can be recalculated for small time intervals, small intervals at theta I minus 1 upon lambda I minus 1. So what is the value of theta I? The value of theta I is here is 0.04 minus 0.02 upon lambda I minus 1 is equal to 1.96958 minus 1.962. So the value of Si will come out to be negative, and that will be minus 5.1640. Okay, so based on the value of the Si, we can calculate the diffusivity, that will be nothing but half times 1 upon Si at particular instance and summation Ai. So 1 by 2 minus 5.1640 into the particular summation of AI is 0.0392. Let's see how much we get. Multiplied by 5.1640 multiplied by 0.5. Okay, so we'll get a diffusibility value of 0.0038, around this one. Okay, so for every value of x you can solve it in a similar manner. Okay, and then you can determine the value of diffusivity at every x. So I would request you people to do it for one more set of data so that you can understand it clearly. Okay, so do let me know if you face any problem while calculating. So now we move on to the shear strength properties in the unsaturated soil, and we for the shear strength properties we basically study two tests. The one is the direct shear box test and the track shear test, right? So here let's understand it with an example. A series of direct shear and soil water characteristic curve tests were conducted for unsaturated clay sand mixture. The results are tabulated in this particular table. Okay, and then we need to determine the shear strength parameters C dash and phi dash, and the functional relationship between the effective stress parameters this xi and degree of saturation S. Okay, this effective stress parameters I and degree of saturation at, and then we need to plot the matrix section and effective stress parameter as a function of saturation. So let's understand what we have here. We have UA minus UW value, we have the degree of saturation value, we have sigma minus UA value, and we have the value of tau, the shear strength. Okay, then we need to calculate the value of C dash and phi dash, and it is the unsaturated clay sand mixture. Okay, so here if you'll note, then the two tests were performed at a matrix section value of 0. It means that by using these two tests we can calculate the value of c dash and phi dash. So while the matrix section is 0, this effective stress parameter is going to be 0, right? And in that case, if we'll this effective stress parameter is going to be 1. In that case, if we'll calculate the matrix section phi is 0, this means u minus uw is 0. Okay, so if you use this equation, then it will become tau f dash is equal to c dash plus sigma minus ua at failure, right, and tan phi dash. So for the first test, if we write, it will be equal to 292 is equals to c dash plus sigma minus ua is 300 tan phi dash, right? First equation. Then we can write the second equation, 141 is equal to c dash plus 120 tan phi dash. Okay, so if we solve these two equations, we will basically get the value of c dash and phi dash. So let's see if we do it for this equation. If we do subtract the equation 2 from 1, we will get how much? 292 minus 141, that's going to be 151 is equals to c dash will cancel out, 180 tan phi dash. So from here we'll get the value of phi dash, that will be tan inverse 151 upon 180. That's going to be 39.99 degrees is equal to 40 degree, we can say. Okay, and if we put this in any of these equation 1 or 2, then we'll obtain c dash. Tan phi dash is nothing but 151 upon 180. So let's see how much c dash we are getting. We are getting 292 minus 300 into 151 upon 180. So we are getting a c dash value of around 40 kPa. Okay, so c dash and phi dash we are getting here, and phi dash is also 40 degrees. Okay, so if we know the value of c dash and phi dash, we can calculate the value of xi f, right? So for the when the matrix section is 0, this value is going to be 0, right? And in case the value of xi f will approach infinity, but by infinity we need a very large value. For xi f, the value ranges from 0 to 1, so the maximum value can be 1. So for this one it's 1, for the second one also it's 1. Okay, so for the third one, let me make some space here. Okay, so if you calculate it, value of xi f, then it will be, we have calculated c dash at 40 kPa, we have calculated phi dash is 40 degrees, and or if we calculate the value of xi f, that's going to be tau f and the value of tau f is 160 minus c dash is 40 minus sigma minus ua value is given as 120 for the third observation, and tan 40 degrees upon the value of u minus uw is 25 tan 40 degrees. Okay, so if we calculate it, let's see how much it is coming. 160 minus 40 minus 120 tan of 40 degrees divides by 25 tan 40. It will be around 0.9204. okay, similarly for this test also we can calculate xi of. It will be 300 minus 40 minus 1, this is 120 tan 40 degrees upon u minus uw is 500 tan 40 degrees. 300 minus 40 minus 120 tan 40 degrees, we have extra bracket, okay, upon 500 tan 40 degrees, so it's going to be 0.379. so here if you'll see, as the value of u minus uw is increasing, the value of xi f will keep on decrease, it will increase. Okay, so there is an inverse relationship between the value of xi f and the value of u minus uw. Okay, so in a similar way we can obtain the value of xi f for all the values of matrix structure, right? So please have a look at how we have solved it, and do let me know if you face any problem. So if we see a similar kind of problem for this triaxial test, then in that case if we realize that only one test at a zero section is required to calculate the value of c dash and phi dash. Okay, and also it is so that because it is a sandy kind of soil, so in that case we can already write c dash as 0. so if we calculate, then we can write in that case we can write the value of sine phi dash is nothing but sigma 1 minus ua and minus sigma 3 minus ua upon sigma 1 minus ua plus sigma 3 minus ua. That's going to be 180 minus 50 upon 180 plus 50, and it will result in a value of phi dash as 34.417 degrees. Okay, based on this, if we calculate the xi of, for first one it will be 1, for the second one if we assume that this phi dash will remain constant and we calculate, then we will get the sigma 1 minus ua value is 220 minus sigma 3 minus ua value is 50 tan square 45 plus 34.42 by 2 and minus twice this one is going to be 0 upon 2 into u minus uw is 10 into tan 34.417, and it will be multiplied by tan 45 plus 34.42 upon 2. Okay, let's calculate this one. So the numerator is 39.98, denominator is let's calculate 1045 plus 34.42 by 2, and this is going to be 26, and if you calculate from 26 it will be there must be some error with the calculation. So if we recalculate again, then you might be getting a value of xi of 0.77. So as the matrix section will increase, this IF value should decrease, right? Please do solve it once to see if the answer is correct. Okay, so with this I think we can jump to the assignment questions for the last week. And the first question reads that the equilibrium sediment volume, that is the free soil volume of the kerosene soil in the presence of kerosene of the kaolin soil in the presence of kerosene is lesser than that of the presence of the water. So in case of the kaolin, if the kerosene is there, and in the presence of the distilled water, if you'll see, the volume is lesser, right? And this volume is lesser, but in the presence of the kerosene the volume is more. Okay, this have to do with the flocculated and dispersed nature of this structure of the arrangement of the particles, right? So the statement that equilibrium sedimentation volume of the kaolin soil in presence of kerosene is lesser than that of the presence of water may not be correct, but it might be true for the bentonite soil. And let's see the second question. The collapse behavior of kaolin soil is physiochemical in nature. So if we see for the kaolin, the collapse behavior is basically physiochemical in nature, because it is because of the it happens at the this atomic level, right? So in that case it can be said that it is true that for the kaolin it is physiochemical in nature. Question number 3 states that the tensiometers are used to measure the soil suction of the soil in the range of 0 to 100 kPa. So as we have discussed in previous lectures also, for the calculating matrix suction, the tensiometers are very good equipments, and they can practically measure suction from 0 to 100 kPa. Okay, and while they age, their range of measurement reduces with time because of the higher entry risk limitations. The fourth question states that the EC5 sensor measures the volumetric water content in soil by using dielectric properties of the pore medium. It is true that in the EC5 sensor, which have been shown here, uh, they measure the dielectric properties of the medium that is in between these two this based on the capacitance principle, and they measure the dielectric properties of the pore medium. Question number 5 says that only drying SWCC of a given soil can be estimated using vapor equilibrium technique. So, to a certain extent, it is true, although it has been said that the wetting SWCC can also be calculated, but the vapor equilibrium technique is primarily used to estimate the drying portion of the soil water characteristic curve. However, it can also help to be determine the wetting portion of the SWCC, though it may not be as straightforward as in the case of the drying process. Okay, so based on this, you can answer this question. The sixth question says the primary swelling nature of the expansive soil in the cell potential versus time plot is due to the diffuse double layer formation. So if we see this part of the primary swelling, that is mainly because of the formation of the diffuse double layers. These diffuse double layers split the particles apart. Because of this the swelling occurs. So this actually occurs in the primary swelling region. So this statement can be considered as true. Question number 7 says in the laboratory estimation of soil suction total suction, dew point potentiometer requires only dew point temperature. So if you'll see here, if we in the laboratory estimation of soil water suction, dew point potentiometer not only requires the dew point temperature, but it also requires the current state of this sample, right? So it does not only require the dew point temperature. So this statement may not be totally correct. Question number 8 states that the kaolin exhibits phase-to-phase particle association when the pH is greater than IEP IEP potential at the edges. So if we see that condition when the pH is greater than IEP, then in that case ion exchange potential at the edges, in that case the arrangement is phase to phase. So it is true in that case the particles are mainly dispersed, so the arrangement is phase to phase. The ninth question says the dew point potentiometer is useful for measuring suction value closer to RH is equal to 100%. So it says that when the RH approaches 100%, conventional humidity sensor may struggle to provide accurate measurements due to the saturation of the water pressure in the air. However, in the dew point potentiometer, the principle is little different. They offer more reliable reading in such condition because it works by cooling of the mirror on the surface or a surface until condensation forms, and then measuring the temperature at which this occurs. The temperature corresponds to dew point, providing a direct indication of the moisture content in the air, right? So this statement is considered as correct. And we have the last question for this week of assignment. So the last question says the 2 gram of the oven dry soil is mixed thoroughly
with distilled water in a measuring cylinder and allowed to settle. The final volume of the sediment formation is measured as 22 ml. And if the specific gravity of the soil is 2.72, we need to calculate the void ratio corresponding to the measured ESP. Okay, the measured sedimentary formation. Okay. So if we see the void ratio, that is going to be volume of void upon volume of solid. If we break the volume of void, is going to be total volume minus volume of solid upon volume of solid. So we can write total volume upon volume of solid minus 1. The total volume is given as 22 ml, and the volume of solid is nothing but gs into rho w upon this mass which is there, right, in grams. So if you write it here, 22 upon gs is 2.72 multiplied by rho w is 1 gram per centimeter cube upon this one is given as 2 grams minus 1. So if we calculate it, we will get 22 into 2, 44 upon 2.72 minus 1. Let's see how much we are getting. We are getting a value of void ratio as 15.17. Okay, so 15.17 is considered as the right answer to this question. So with this, we have covered all the week of the problem solving session of this particular course, and thank you everyone for joining. If you may have any questions, kindly do drop me a mail or ask me in the live class, and I'll be here for a while to if you people have any questions. Thank you.